Okay, so now we're going to actually talk about how ATP is made through the enzyme ATP synthase. So when you look at the electron transport chain, or if you look at an image of the electron transport chain, they're going to show you have 4 enzymes associated with electron transport chain, and then you're going to have a 5th enzyme that's going to be associated with ATP synthesis, and so it's called ATP synthase. Now, the electron transport chain is what's going to generate the proton concentration, and you're going to have a higher concentration of protons in the inner membrane space as compared to the matrix. And so this charge difference across the membrane is what's going to drive the proton motive force. And the proton motive force is what's going to drive the synthesis of ATP. And so ATP synthase is the enzyme that's going to pick up the protons from the inner membrane space and bring them and release them into the matrix. And this flow back through the ATP synthase into the matrix is going to generate ATP. So ATP synthase is an enzyme that is going to span the inner mitochondrial membrane. And you're going to have 2 parts. You're going to have the F1 portion, which is going to extend into the matrix. And this has the alpha beta subunits, and these are going to catalyze the formation of ATP. And it's the beta subunit that actually forms the ATP, and the alpha subunit is there for structure. Now there's also the F0 portion, which is the portion that actually spans the membrane. And this is what's going to pick up hydrogens. And the hydrogens are going to be picked up in the inner membrane space, and they're going to be released in the matrix. Now for the F0 portion, you're going to have carbon subunits. That's what these C's are. There's going to be 12 of them, and they're going to form sort of like a rotor, and they turn. The shaft of the rotor is going to be made up of epsilon and gamma subunits, and you're also going to have a linker. So you have a delta and the B2 portion that's going to link the F1 and F0 pieces together. This headpiece held by the delta subunit attaches to that beta 2 subunit, also having a membrane spanning domain, and this attaches to the A subunit here. Now for ATP synthase to work, you have to have the protons enter the matrix between the A and the C subunits. And so the carbon subunits, remember the C subunits make up sort of the rotor, and the A subunit is going to be a membrane spanning domain. And so you're going to get hydrogens that enter, and this is showing how they enter sort of this C subunit here, and then eventually you're going to have them exit. So the C subunits are going to pick up the hydrogens. The reason the C subunits do this is because they have a glutamyl carboxyl group that extends into the proton channel, and this is what actually accepts the protons. Now the channel is going to be continuous, and it's going to be open both sides, open to the matrix as well as the inner membrane space. And it's the concentration of hydrogen, high levels of hydrogen on the inner membrane space that drives its movement and attachment to the carbon subunits at the glutamyl carboxyl group. And then it's going to be the low levels of hydrogen in the matrix that are going to facilitate the release of the hydrogen into the matrix. So once you have the C subunit accept the proton, you're going to have a rotation into the lipid membrane. So remember, we're still dealing with a membrane, so there is a hydrophobic region. And so the proton on the other side in the matrix is going to be exposed, and it's the low proton level of the matrix that allows the glutamyl carboxyl group to release the proton. And you're going to have the rotation that's going to be complete with the attraction between the glutamyl group, which is negative, and the arginal positive subunit, positive group on the A subunit. So again, all has to do with charges. Remember that the matrix is going to have fluid, so the glutamyl subunit is a negatively charged, will be fine in an aqueous environment. and then it'll be attracted to the A subunit with that arginal group, so you can keep the rotation going in this C subunit motor system. Now what happens to make ATP? Well, the ATP is on the alpha-beta portion of the ATP synthase. So this is the F1 complex, and it has three sort of little flower clover-looking units shown here. You're going to have the beta portions are going to be binding to ATP tightly if it's in the beta ATP conformation. If it's in the beta ADP conformation, it binds loosely. And then there's also a beta subunit that's empty. Now keep in mind the alpha is not going to participate in the binding of ATP or ADP. It is there just for structure. So in essence, you're going to have your ATP binding here at the beta subunit, and then you have it released. ADP will bind, and an inorganic phosphate will be added to it, and this is going to form ATP and be released. And so this sort of just cycles through these three different conformations. Now overall for ATP synthase, there are 12 carbon subunits, so 12 protons are going to be needed to fill up those carbon subunits, and this is going to generate one turn to make 3 ATP. So you need 4 protons for each of the ATP that are going to be made.